Lesson 28 reviews the design strength of structural bolts. This includes both their shear and tensile strengths. Remember, the bolt is transferring a force or load between two elements of a connection. In structural steel connections, bolts can be subjected to either shear or tensile loads or a combination or both. When the connection subjects the bolt to shear, the load transfer can be either by bearing of the bolt holes against the bolt shaft or by friction between the plate or vane surfaces as a result of the clamping action from the bolt preload. The shear loading may be subjected to both single shear or double shear. This refers to the number of shear planes that develop in the bolt that resist the applied shear force. We will see that the location of the threads with respect to the shear planes will affect the bolt shear strength. Shown are bolted connections subjected to shear. The load transfers through the connection by the plates bearing on the bolt shafts. The upper connection subjects the bolt to what is called single shear, as only one shear plane will form in the bolt shaft. The lower connection subjects the bolt to what is called double shear. In this case, the two shear planes form in the bolt shaft to help resist the shear force. Since two shear planes must form to fail the bolt has double the strength than the same bolt subject to single shear. Note that in order to have double shear, you must have a main plate sandwiched by two side plates. The sum of side plate thicknesses is usually equal to or greater than the thickness of the main plate. Shown is a high-strength bolt that was subjected to double shear. You can see the location of the two shear planes. There was some rotation and bending in the bolt due to the play or gap in the bolt holes from the 1/16 inch standard oversize. When the connection is designed as slip critical and the bolts have been properly tightened and preloaded, the load transfers not by bearing, but rather by friction between the vane surface. You can have either single or double shear slip critical connections. As with bearing type connections, the double shear has double the strength of single shear. For the two types of high-strength bolts, you have three possible load conditions in shear. Two thread conditions occur for bolt bearing type connections. One is if the threads are not located in the shear plane or excluded from the shear plane and designated as X. The other is when the threads are located in the shear plane or are not excluded and are designated as N. High-strength bolts can be purchased with different thread lengths for a given overall bolt length. For slip-critical bolts, there is only one designation, which is SC, since the bolt is transferred by friction between the vane surfaces. Therefore, shear planes do not form, and the location of the threads is irrelevant. Note that for a given bolt type, that is either A325 or A490, it can have three different strength values. Add in the possibility of single or double shear, you are now up to 6 different strength values. You will see the use of XN or SC designation after the bolt type. You need to look at the connection to determine if the bolt is in single or double shear. Unfinished bolts, A307 bolts, are assumed to be fully threaded, so you don't have to have the included or excluded issue, and they don't have enough strength for them to be preloaded. Therefore, there is no designation following their bolt type. Separate ASTM standards were developed for the twist-off tension control bolts. These have the same strengths as A325 and A490. AISC then puts the bolts in groups. Group A has A325 and F1852 bolts, and Group B has A490 and F2280 bolts. Group B bolts have higher strengths than Group A bolts. The formula to determine the shear strength of bolts designed for bearing is shown in this slide, which is an expanded version of AISC equation J3-1. Note the use of the lowercase r stands for the strength of a single bolt. A capital R is used to represent the strength of the entire connection or the sum of the individual bolt strengths. The term uppercase N sub SP is the number of shear planes. Note that the area of the bolt is based on the nominal diameter of the bolt. For us, that would be 3/4 7/8 inch. If the threads are in the shear plane, then there is a reduction in the bolt diameter, but this is taken care of by the last term listed, that is F sub NV. F sub NV is the nominal shear strength of a bolt in units of KSI. This value is obtained from table J3.2 of chapter J, where much of the connection provisions are located. Shown is table J.2. Several things here to note. Both the tensile and shear strengths are given for the various bolt types. We will discuss the tensile strength of bolts at the end of this lesson. For Group A and B bolts, two shear strength values are given based on whether the threads are included or excluded, or what is called the thread condition. Note the shear strength values for threads not excluded from the bolts are lower than those values where the threads are excluded. The reduction is approximately 80%, which means the reduction in area due to the threads in the shear plane is approximately 80%. For A307 bolts, only one shear strength value is given, since it assumes that the threads are always in the shear plane or they're not excluded. As always, if you want to do something in steel, there is a table for that. Table 7-1 provides strength values for single bolts subjected to shear. Note that groups A and B are listed in addition to A307 bolts. Groups A and B are divided into two for the thread conditions X and N, which are then divided again into single shear and double shear as indicated by the uppercase S and D. The A307 bolts are only divided for single and double shear. Additional information is given in the table, such as the gross diameter and the design shear strength, which are values obtained from table J3.2 with the reduction factor of 0.75 applied. Note the available diameters for these bolts range from 5/8 to 1.5 inches. As previously mentioned, the common diameters for structural steel are 3/4 and 7/8 inch diameters. You can make use of this table in this class to get your shear design values for bolts. You do not need to use the formula previously shown unless specifically asked to do so. As mentioned before, the load transfer method for slip critical connections is by friction between the fane surfaces. The condition or preparation of the plates or fane surfaces affects the magnitude of these forces, as this will affect the coefficient of friction. To get the proper frictional force between the plates, the bolts must develop a tensile force of at least 70% of its ultimate tensile strength. The four tightening methods previously discussed are intended to achieve this. The formula used to determine the slip critical value is different than the formula used to determine bearing values. Again, This formula calculates the slip critical design strength of a single bolt. Note the use of the term slip planes. This is similar to the number of shear planes, but slip is used since the bolts do not go into bearing nor form shear planes. The combination of the tensile force in the bolt times the coefficient of friction gives you the frictional force. This is the same as mu times the normal force you should remember from your statics course. The minimum fastener tension is given in AISC table J3.1. Two values can be used for the coefficient of friction and are designated as Class A for a value of 0.30 and Class B for a value of 0.50. The conservative value is 0.30, which is Class A, which we will use in CVN 446 unless advised otherwise. The term uppercase D sub U is an adjustment factor and has a value of 1.13. Filler plates are thin plates that are used in bolted connections to make up thickness differences between connected elements. This increases the sum of the gaps between the plates and makes it more difficult to tighten the connection and get the proper preload. Two coefficients of friction are specified for structural steel, 0.30 and 0.50. A Class A surface has 0.30 coefficient value and is used when only minimum preparation of the fane surfaces is performed. This is where the mill scale has been cleaned and the surfaces are free of debris. This can be done by hand. Class A is also used when the surface has been blast cleaned and galvanized using the hot dip process. The galvanic coating needs to be roughened, and otherwise the surface is too slippery and the coefficient of friction is reduced. Class B surface has a 0.50 coefficient value and hence a higher resistance to slip than Class A. However, more preparation of the fane surfaces are required. This involves sandblasting the surfaces, and they cannot have any coating such as paint or zinc. To account for the type of hole, a varying reduction factor is used. The hole type affects the slip critical shear strength since the fane surface, and that's where the friction develops, is reduced by the amount of the surface area removed by the hole. For standard holes, which have the typical 1/16 inch oversize, as well as short slotted holes perpendicular to the applied force, have a resistance factor of 1. When oversized holes and parallel short slotted holes are used, the reduction factor is 0.85. And when long slotted holes in either direction are used, the reduction factor is 0.70. This slide shows the different hole types and summarizes when each can be used. Note that if the hole is slotted, the slot must be perpendicular to the applied force if the bolt is designed for bearing. This has only the 1/16 inch oversize in this direction and behaves no differently than a standard hole. The corresponding resistance factors are also given in this slide. Shown in this slide is a typical table for slip critical bolts. Note that this table is specific to Group A bolts. Those are the A325 and the Class A fane surface. Slip critical shear strengths are given as a function of the hole type as well as the number of shear planes and the bolt diameter. The continuation of Table 7-3 provides the corresponding values for Group B bolts. There are no tables provided for Class B fane surfaces. Now, let's turn our attention to bolts subjected to tension. While most bolted connections load the bolts in shear, there are still connections where the bolts will load into tension. This includes what are called hanger connections and connections subject to bending or eccentric loads. Bolts in tension will always fail in the threaded section of the bolt shaft. However, in the formula to determine the design tensile strength of a single bolt, the gross area of the bolt is used for consistency. An adjustment has been made on the nominal tensile strength to compensate for this. The nominal tensile strength values are given in AISC Table J3.2. That's the same table as the nominal shear strengths. The tensile design strengths are given in AISC Table 7-2. Note that the table is rather simple when compared to Table 7-1. This is because it doesn't have to deal with the thread condition nor the number of shear planes. This ends Lesson 28.